All right, folks, these are going to be long videos. Sorry, not much we can do about that. Okay, so we're getting to the points I told you in class that graphing these buggers can be worth a lot of marks. And the reason is you have to look for all of these checks. Start off with your asymptote checks. Then from the asymptote check, you might look to see if there are any holes if you simplify equations, and holes would knock out one of the asymptotes kind of thing. You'd make that statement. The x and y intercepts often are, related to asymptotes and holes. So check for everything. And then depending on the type of graph, you might have to check your end behaviors close to the asymptotes. You might have to average the asymptotic value to be able to find like a local maximum or minimum. If it's one of those rationals that looks like a quadratic in the middle, it's got a parabola part. You've got to find how high and low those go. And then an interval table is probably something you're always going to use, and there probably will be a mark associated with that like all of the time. So what do I want to see? This. It depends on the graph for this one. So that gives you an idea. Okay, we're going to do it. We're going to sketch it. We're going to go through all the steps. Get ready for it. Okay, start with the asymptotes. Vertical asymptote, x equals 3. Okay, horizontal asymptote. If I put in a really big value of x, it would go to a really big value in the denominator, and the numerator would always stay 2. So it's approaching 0. Horizontal asymptote, y equals 0. Okay, that tells me also my domain and range. Oblique asymptote. Oblique asymptote exists if the degree of the numerator is exactly 1 higher than the degree of the denominator. Not applicable. Okay. Checked those things. Then go to see if there are any holes. Well, no holes. No holes. Since numerator can't be factored. You'd have to be like, it literally would have had to look like something was factored, and we would have had to get that to be able to say there's a hole. Like, it's just a 2. So there are no holes for this one. But be patient, my little students. No hole since numerator can't be factored. And y'all know me. Still say don't cheat. No, sorry. I need to go and start graphing this stuff because you know I make mistakes all of the time, like it's my job. There's one of them. How's that look? Oh, not quite a vertical. There. Oh my, Megan. There. Jeez. This is Don't do it. Don't choose violence. Don't do it. Don't choose violence. You're good. Good. X equals 3. Oh, I'm at the top. This is a vertical asymptote. Okay. Okay. Then horizontal asymptote y equals 0. Horizontal asymptote y equals 0. Pink. No. Let's go horizontal asymptote y equals 0. Okay, so I know one of the values we're going to be testing is 3 if we're less than or greater than. Okay, no holes, numerator can't be factored. Where am I at? Let's do x and y intercepts. x int let y equals 0, 0 equals 2 over x minus 3, multiply both sides by x minus 3. Can't happen. Therefore, no x-intercept, which makes sense because that's where the horizontal asymptote is. So your graph is never going to cross at like the x values. Okay, so makes sense. We just proved it mathematically. Let's find our y-intercept. So wherever I see an x, I'm going to plug in a 0. 0 minus 3. Ooh. Negative 2 over 3. Therefore, y-intercept at 0, negative 2 over 3. I'm going to plot that. 0, negative 2 over 3. 0, negative 2 over 3 is 0.666 there. Negative 2 over 3 is negative 0.6666. Okay, I'm happy with that. I have a feeling it probably does something like this then. That's my guess. Let's just get more information. Well, we could look at the transformations. This is a reciprocal graph that has been vertically stretched by a factor of 2 and has been horizontally translated to the right 3 units. Okay. Then end behaviors. Let's find out what's happening close to the intercept. We know there is a vertical asymptote. Sorry, the asymptote, not the intercept. The vertical asymptote's at x equals 3. So let's find out end behaviors. Oops, daisies. Oh, you don't do it. Slow down the writing. So if 3 is our value, my preceding is going to be 2.9 and my following is going to be 3.1. So f of 2.9 is going to be f of 2.9 is going to be 2 over 2.9 minus 3 equals 2 divided by 2.9 minus 3 is going to give me a negative 20. So it's going down negative. So that means on this side of the asymptote, we're going down, which makes sense. Okay. I'm feeling pretty confident right now to, and I know it's been vertically stretched by a factor of 2, so I'm going to match those up, and I'm just going to start showing that that is approaching the asymptotes. Good. Then let's check for f of 3.1. I'm hoping this is a really big positive number, 3.1 minus 3. 2 divided by 3.1 minus 3. Oh, positive 20. Bingo bango. So as it's going here, the graph is going up positively because we saw that you've got that positive 20 down here. Okay, so we know this is how we know it's been vertically stretched by a factor of 2. She's going to go like that. Now you could create an interval table for this one, but we have done so much graphing that we already know what this is pretty much looking like. The way the interval table would look, though, would be I would go numerator, denominator, ratio. That's just like numerator sign divided by denominator sign. And then our value is, what is it, 3? So we're testing a 2 and we're testing, whoops daisies, putting them in the wrong spot. We're testing a 2 and we're testing a 4. And the numerator is always going to be positive, positive. The denominator here, that's when you would end up getting a negative and you get a positive there. So it tells you that the ratio here is negative on from negative infinity to 3. It's in y negatives. This is why I don't make long videos, because I start rambling. This is positive. So from 3 to positive infinity, your f of x is going to be greater than 0. Okay. Nice. Okay, stop the recording.